And now we're thinking about electric forces. Uh, uh, Electric phenomena are a little bit new, not like things that we've seen before, but we're still talking about forces. So Newton's laws still matter, acceleration and all that. But start with the basic idea. Uh, Charge, we can basically think of as just some property that some things have. And if they have that property, it allows them to feel this particular kind of force, electric force. And like any force, you divide it into two parts, a direction and a magnitude. Direction we take care of just by remembering like charges repel each other, unlike charges attract each other. So imagine here's two charged particles and they're a distance d meters apart, and let's say they both have the same type of charge. They're both positively charged or both negatively charged. So both have the same kind of charge, they repel each other. That means 2 feels a force from 1 pushing it straight away from 1. So there's the force from 1 on 2. And then 1 feels a force from 2 pushing it straight away against, straight away from 2. So there's the force from 2 on 1. That's how we deal with directions of electrical forces. Unlike charges repel, unlike charges attract, and like charges repel. Here's the rule for magnitude, strength of an electrical force. I'll usually refer to it as Coulomb's law. So the magnitude of the force from one thing on a second charged thing just obeys this formula. This capital K is a constant factor that you can look up in the Coulomb's law section of chapter 20 if you need to do any calculations. In this slot goes the magnitude of the source of the force, charged object 1, and then in this slot goes the magnitude of the charge on the thing that's feeling the force. Right? This is an equation for the magnitude of a force on 2. Right? Object 2 feels this force. So this is the slot for the charge that is the source. This is the slot for the charge that is feeling the force. What if we switch things around? Instead of a force from 1 on 2, we look at a force from 2 on 1. Now, 2 is the source, so 2's charge goes in this first slot. That's the source slot, just like 1 was the source in this case. So charge 1 goes in the first slot. And now this is a force on 1, so the charge of the thing that feels the force goes in the second slot here, just like the thing that felt this force, thing 2 felt this force, so thing 2's charge goes in the second slot. But now compare this force to this force. In the numerator of both, you've got the same product. Absolute value of charge 1 times absolute value of charge 2. And then here you've got absolute value of charge 1 times absolute value of charge 2. The numerators are the same. And we're not, and we're measuring these two forces at the same point in time, so it's the same, certainly the same distance in both cases. So what do we have? We have the magnitude of the force from 1 on 2 is just equal to the magnitude of the force from 2 on 1. These two forces are the same type of force, They're both the electric force, the Coulomb force. They're both the same strength, same magnitude. They're pointing in opposite directions, and in one force we have a force from one thing acting on a second thing, and then the source and the receiver of the force are flipped around in the second case. The source of one force receives the other force, and the thing that felt the first force is the source of the second force. Right? Source and receiver are flipped around as you go from this force to this force. What does that pattern sound like? You've heard it before. That's how you describe a Newton's third law pair. These forces are a Newton's third law pair. The important thing to remember about that is that being a Newton's third law pair, they are the same strength, period. No matter how much charge is on this one and how much charge is on this one, there might be a million more units of charge on this one than on this one. They might have very different values for their Q's, but no matter how different Q1 and Q2 are, those forces are a third law pair, so they're always equally strong. That's one of those things that's easy to say, but sometimes difficult to remember. You have to make an extra conscious effort to remember that. It's not necessarily going to be the first thing that pops into your mind when you see two objects with different charges interacting with each other. You've got to make that extra conscious effort to remind yourself that those two forces are a third law pair, so no matter how different the amounts of charge are, the forces are equally strong. Okay, let's just look at a couple things here. If we keep those two charged objects, maintain the same amount of charge on them, but just move them around, then everything in the numerator stays constant, only the denominator here changes, and in that case we've got inverse proportionality. Right? One variable equals constant stuff divided by some other variable, where the one variable is the magnitude of the force. The constant stuff is k and then the product of the absolute values of the two charges. Remember, we're talking about just the magnitude of the force, not the direction. So that's why we have absolute values here. We don't care about the sign of the charges when we're thinking about magnitude. We care about the sign of the charges only when we're figuring out the direction of the force. And so, remember, this equation tells you that everything on this side of the equation that is not a constant factor is going to be the variable that's proportional to the other, inversely proportional to the other variable. So everything on this side of the equation that isn't a constant factor is d squared. Not d, but d squared. Unless you say d squared, you haven't named everything that is not constant on the right side of the equation. So we have a proportionality between the magnitude of the force and inverse of the distance squared. So for example, let's say two things are separated by d meters. And then you squeeze them closer together so that now they're only half as far apart, d over 2 meters apart. So d has changed, therefore anything that it's inversely proportional to must change. And specifically, in inverse proportionality, if this variable d squared changes by some factor, the thing it's inversely proportional to changes by the inverse factor. So we know how d changes, but in order to figure out how the magnitude of the force changes, we need to know how d squared changes, because that's what's proportional to the magnitude of force. That's what has the proportionality relationship with force. But we can figure that out easily. The second distance is just 1/2 of the first distance. But we want to know how the square of distance changes. That's easy to figure out if we start with this equation. Just square that whole equation, and then we'll have a relationship between square distances. So on the left-hand side, after you square things, you've got square of the new distance, square everything on the right side, and you have the square of 1/2, that's 1/4, and then square of the old distance. So the variable called d squared, when you go from the old value of d squared to the new value of d squared, changes by a factor of 1/4, which means force, being inversely proportional to d squared, changes by the inverse of this factor. New force is 4 times the old force, or the magnitude of the new force is 4 times the magnitude of the old force. And then similarly, if you pull them twice as far apart, making the distance twice as big as it was in the first case, you'll get a smaller force. And how much smaller? So you start out with them a distance d apart, and then separate them more, and so they're a distance 2d apart. That is, the new value, the new distance is twice the old distance. Since distance changes, distance squared will change, and the factor by which distance squared changes will tell us the factor by which force changes, because force and distance squared are inversely proportional. If we know how distance squared, we can just square this equation to figure out how, if we know how distance changes, we can figure out how distance squared changes just by squaring this equation. So square of the new distance equals square of this, 4, times square of the old distance. The variable called distance squared changed by a factor of 4. So magnitude of the force, being inversely proportional to d squared, changes by the inverse of this factor, 1/4. New force, magnitude of the new force is 1/4 magnitude of the old force. Handy thing to remember in a lot of the exercises and questions and problems that you'll be dealing with. Got 2 charged particles and they're exerting a force on each other. If the distance doubles, the force is reduced to 1/4 of what it had been. And then similarly, if you got the 2 charged particles and you squeeze them together so that now they're only half as far apart as they were, the magnitude of the force gets 4 times larger. All right, important to remember that don't make this mistake. If you separate things twice as far, that doesn't cut the force in half. It cuts the force down to 1/4 of what it had been before. So let's look at a couple situations where we have to think about that. So let's imagine this. We've got three charged particles. It's a positive one, and then another positive one, and then another positive one. To keep things simple, we'll say that they're all evenly spaced. Right? This distance is the same as this distance. And again, to keep things simple, we'll say that they all have the same amount of charge. One positive sign here and another positive sign here means not only that they're both positively charged, but they have the same amount of positive charge. Right? If I want, say, this one to have more positive charge than this one, I'd signify that by writing more positive signs on this one. Right? If I wanted this one to have 3 times more charge than this one, I'd write this one with 3 positive signs in it. So anyway, let's think of these as left, center, and right. What can we say about the net force on the right-hand charge? Net force on the right-hand charge. Let's think of this algebraically. And of course, we'll need to compare the net force on this is, of course, a sum of the force from the center plus a force from the right-hand charge. Force from the center charge on the right-hand charge plus the force from the, it's getting a little dyslexic here. This is on the left. We're looking for the net force on the left-hand charge. And this one is the source of a force from the right-hand charge on the left-hand charge. Okay, that's better. Well, 2 parts here. We have to think about magnitudes and we have to think about directions. I suggest that we always start by thinking about directions first. They're all the same type of charge, so they all repel each other. We're thinking about the force on this one, so this is going to feel a repelling force from the center charge, and it's going to feel a repelling force from the right-hand charge. If this one is getting repelled by this one or this one, that means this charge on the left is being pushed farther to the left in order to be repelled by these charges here on the right. So if we think of right as the positive and left as the negative direction, the force from this on the left-hand charge is negative, pointing in the negative direction. The force from this is negative, pointing in the left-hand direction. Okay, so the net force is just some amount of negative force, and then you add on some more negative force. Well, how much force here, how much force here? All we can do there is say what the relative strengths of these 2 forces are. We don't have enough information to calculate the actual value, but we can think about relative strength this way. Here's 1 unit of charge. Imagine the force from the center charge on the left charge. 1 unit of charge acting on 1 unit of charge, and they're just separated by 1 step. We'll call that much force just plain F. That is, when I say F, that will mean just the magnitude of a force from 1 unit of charge acting on a second unit of charge, just 1 step apart. Of course, these could be either positive or negative. What's important here, since we're talking about the strength, the magnitude, the size of a force, is the size, the absolute value of the charges, not the sign. So we could just put a plus or minus in here. It's plus in this case, of course. So to repeat, the charge from 1 unit of charge acting on 1 unit of charge 1 step away we will just call F. And that 1 unit of charge acting on 1 unit of charge one step away describes the force from the center charge on the left-hand charge. So it has a magnitude of F, and it's pointing towards the left, the negative direction. Now what about this? It's the same amount of charge acting on the same amount of charge as before, but now the distance has doubled. If we don't change the charges, but we double the distance, we know what happens. You double the distance, while keeping the charges the same, you have cut the force to 1/4 of its previous strength. So the force from the right-hand charge on the left-hand charge is 1/4 as strong as this force, because this force is twice as far away as this force. So the net force on the left-hand charge, in this case, is minus 5/4 F. That is 25% larger than the force you would get from just one charge one step away. And look at another example. Different signs make it a little bit more complicated. Let's say we'll still look for the net force on the left-hand charge. Now a negative charge is in the center, but then a positive charge is on the right. It's still the case that the net force on the left-hand charge is a sum of two forces, the force from the center on the left-hand charge plus a force from the right-hand charge on the left-hand charge. Start by thinking about directions again. So the force from the center charge on the left charge, center and left charge have opposite signs, so we have attracting forces. The force the left-hand charge feels, the force on the left-hand charge, is an attracting force. It is pulled towards the source of that force. So this is pulled to the right by this. So the force from this on this is a force to the right, in other words, positive direction. And then this, the one that's farther away, has the same sign as the left-hand charge, just like it did in the previous example. Same type of charge means they repel each other. This one is repelled by this one. In other words, this one pushes this one away, farther away, towards the left, which is the negative direction. That's the sign. The magnitudes are just the same as they were in the previous case. Here, you still have 1 unit of charge acting on 1 unit of charge one step away. So the magnitude is still F. And in this case, the source charge is 1 unit of negative charge, and the thing that feels the force is 1 unit of positive charge, but it's still 1 unit of charge acting on 1 unit of charge one step away. We call that much force F newtons. The only difference now is that it's F newtons pulling this to the right, whereas in the previous example it was F newtons of force pushing this one to the left. And this one, being twice as far away from the left-hand charge as this one is, has a force that's only 1/4 as strong. You double the distance, you cut the force down to 1/4. So the strength of this force, the force from the right-hand charge on the left, is 1/4. 1/4 the strength of this one. So now, what do we have? In this case, the net force acting on the left-hand charge is the sum of these two, which is positive 3/4 F. In other words, the net force acting on this one, the net result is that this one is pulled to the right. Net force points in the positive direction. The strength of that rightward pull is only 75% of the strength that you would get from 1 unit of force or 1 unit of charge one step away. Right? If the middle charge, the center charge, the negative charge were the only one acting on the right-hand positive, left-hand positive charge, the net force would be just plain plus F. But now you've got this applying a little bit of leftward negative repelling force, so the net force is a little bit weaker than that. And then one last example. Let's say now we're switch things around a little bit. Let's think about the net force on this one. Net force on the right, which is a sum of the force from the center charge on the right plus a force from the left-hand charge on that right-hand charge. So, signs first. The center charge and the right-hand charge are opposite, so they attract each other. That is, the force on this coming from this is an attracting force. This force, this charge attracts this charge. So this charge is pulled closer to this charge. Pulled to the left, in other words, which is the negative direction. And then this charge here on the left, which is farther away, has the same sign as this, same type of charge, so they repel each other. That is, this one repels this one. The left-hand charge applies a repelling force to the right-hand charge, so the left-hand charge pushes the right-hand charge farther to the right. A rightward push is a positive push, a force in the positive direction. So there we have it. And now what about magnitudes? Just like in the previous case, this is 1 unit of charge acting on 1 unit of charge 1 step away. That's the amount of force that we call F. And then this is twice as far away from the right-hand charge as this one was. So this applies a force on the right-hand charge that is only half as strong as the force from this one. Force from this one, or sorry, 1/4 as strong. This one had a force of magnitude F, so this one applies a force with a magnitude 1/4 F on this one. So as a result, the net force is minus F plus 1/4 F, or minus 3/4 F. The net force is in the negative direction, so the net result is that this charge feels a leftward push, but the magnitude of that leftward push is less than what you'd get from just 1 unit of charge 1 step away. It's 25% less than the force you would get from 1 unit of charge 1 step away. A force of just plain minus F is the net force on this one if the center charge were the only charge. But now with this one, in addition, it counteracts and cancels out some, but not all, of the force that came from this one. All right, now you can try some.